Oh. All right, y'all, so let's get started. So we're going to continue talking about our transition metal complexes today, but we're going to introduce sort of the geometries of these complexes, and more importantly, what's called crystal field splitting, crystal theory, okay? Crystal field theory, there she is. All right, so crystal field theory. All right, so somebody asked a very good question, which is like, well, what's the difference between these coordination bonds that we see in our transition metal complexes versus like a polar bond, or rather a covalent bond? Both of them involve the sharing of electrons, right? So what's the big difference? And really, it kind of boils down to the theories that we use to talk about these concepts, right? So covalent bonds, there's nicely explained by molecular orbital theory, where you can use quantum mechanics and these wave functions, you can combine them and they make these molecular orbitals, blah, 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 a little bit above the pay grade of this course, but the bottom line is there's this nice, neat little theory, well-founded in quantum mechanics, that is used to explain covalent bonds, okay? Transition metal complexes, that theory didn't quite work. It didn't quite explain everything, right? So they had to come along and build this new theory, what they called crystal field theory, and this helps explain two important properties of our transition metal complexes that aren't explained by that just covalent bonding theory, okay? And these two theories that we're going to see explained is the color of these complexes, as well as their magnetic properties. All right, these two things are well explained by this crystal field theory, whereas covalent bonding theory just fell short. It didn't explain these, okay? So first of all, color of complexes. What do I mean by that? So, turns out that our transition metal complexes tend to be very brightly colored, pretty solutions, right? So transition metal complexes, they're brightly colored, which really means that they absorb photons in this region of the electromagnetic spectrum that we can see with our eyes, the visible region. All right, other covalently bound complexes, they tend to not be very brightly colored at all. And the ones that do always share this same property of having a lot of double bonds in there, a lot of carbon-carbon double bonds. So again, covalent bonding theory just didn't really explain why these transition metal complexes have these like bright, beautiful colors that they do, and crystal field theory does. Okay, and the other thing is the magnetic properties of these complexes. Anything that has any magnetic properties is because it has unpaired electrons. That's what we call paramagnetic. All right, and so again, covalent bonding theory just didn't explain all these obvious magnetic properties. Magnetic properties are really easy to test, right? Does it respond in a magnetic field at all? So they had all these complexes that have all these sort of magnetic properties. They can tell that there's unpaired electrons in them. Covalent bonding theory didn't explain it. So again, that's why this new crystal field theory was built, helps explain why there are all these unpaired electrons in our transition metal complexes. Okay? All right, and we'll show how to build this theory here in a second. All right, we got to sort of go step by step here. So, first of all, given a complex. We said that there are two things that you should be able to tell me from this formula. One is the oxidation number. And the other was called the coordination number. All right, so copy down this formula. We're going to go back to our constants page. So everybody take a second. Given this chart here, you should be able to tell me the coordination number of this complex, as well as the oxidation number. 6. All right, so the oxidation number here would be what? +3. Water is a neutral ligand. There's no charge associated with that water. So the charge on that metal ion is just that +3. All right, and then what's the coordination number? What do I mean by coordination number? The amount of donors, right? So there's 6 water molecules all stuck to this transition metal. Each water can donate at just one single site. So that means my coordination number is 6. Okay, and then the last thing that we want to do is, given this oxidation number of titanium, right? This is a titanium 3+ ion. Let's use our periodic table. And everybody's going to take a second and give me the electron configuration of this titanium 3 ion. All right, we're going to see a lot of the skills that we kind of laid out first being rolled up into one here. All right, so if I was just doing titanium all by itself, I'm going to use the abbreviation that's argon. And then I also have 2 4s electrons, 4s2, as well as 2 3d electrons. So then if I go to the titanium 3 ion, now I'm going to start pulling electrons from that configuration. And which are the first ones to go? The 4s. I still got one more I got to remove, right? Because I got to remove a total of 3. So that last one's going to come from that 3D, leaving it with just one 3D electron. Okay? All right, so now we got all these little components that we sort of worked on individually. That's my electron configuration and our coordination number. Okay. Our coordination number will help us figure out the geometry of our complex. Okay, we need to first figure out the coordination number. Once we get the coordination number, that will help us figure out what the geometry of this complex is. All right, so going back here, we got 4 options for our geometry, all right? Let me make some space over here. Okay, and these will correspond again to our coordination number. If you're linear, how many ligands would you have bound to that central transition metal? Just 2, right? One over here, one over here. What about tetrahedral? How many ligands? 4. And actually the same thing with square planar. We'll learn how to distinguish between these two here in a bit, okay? But then an octahedral, despite the name octa, is 1, 2, 3, 4, 5, 6 ligands. So a coordination number of 6 would correspond to which geometry? Our octahedral. Okay? So our transition metal complex, we were given this formula. We were able to tell a few things from that. We had this titanium 3 ion, that was our oxidation number. So from there we could figure out our electron configuration. And we had this coordination number of 6, which led us to determine that we have an octahedral geometry. What's up?
Would this compound also be a hydrate?
It is not a hydrate. It's considered a hydrate is a neutral ionic compound that has water molecules bound. This is just the ion. Okay, so now we're going to get into our crystal field splitting. All right. So what happens is we have, if you remember back, we were talking about these atomic orbitals, the 1s2, 2s2, blah, 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 right? Those d orbitals have 5 suborbitals. All right, so this is my 3D. And they all had these like fancy names associated with them. It's not really that big of a deal to know them, but the XY, the YZ, the XZ, Z squared, and then X squared minus Y squared. All right, these were these lobes of these suborbitals of the 3D, right? And they all correspond to these different geometries. Right? Most of them, 3 out of the 4 or 4 out of the 5 are these like clover-shaped ones. And then you had the one weird one, which was the peanut shape with the donut around it. All right? But these were these 3D orbitals. 2 electrons can live in any one of these orbitals, right? So when you filled in these diagrams, you would fill them in with these electrons, half fill each one first, then go back and double up, for example, right? That's what these diagrams were. Each one of those boxes represented one of these different lobes here, one of these different orbitals. Each one could contain 2 electrons. All right? So we're going to see something similar here, except for now we're not just going to be working with these atomic orbitals, but we're going to say that they split. All right, so these were my atomic orbitals. Now we're going to draw the same thing, but for our complex. All right, and it turns out that as soon as you stick all those ligands around, all those water molecules around, these atomic orbitals split in energy. Some of them increase in energy, others decrease in energy. Okay? And so what we're going to see is now we have 3 lower energy orbitals and 2 higher energy orbitals. All right. And again, you don't really have to know the names of which is which, but just to kind of put it down. So these ones are now our lower energy orbitals. Oops. And these two have increased in energy. All right. And this is explained if we look at the shapes of each of these orbitals. Remember, if we have an octahedral, we have how many ligands? 6. If we put those 6 ligands around, we can see that for these top two, those ligands are located directly next to these lobes, these electron orbitals, increasing their energy. Versus the other 3, they're kind of spaced out more evenly where they're sitting in between them. And so that's why these are lower in energy. All right, so again, what explains this splitting in energy is simply the proximity of the ligand to the orbital. Close means that it's higher energy. So the ones that are further away are lower in energy. All right, so real quick, I know that this picture is very confusing, so let me just boil this down to the punchline here. What do we really need to be able to do? Okay, for an octahedral geometry, that's what we said that we had. Our complex orbital splitting, octahedral, has 2 high energy orbitals and 3 low energy orbitals. All right. What are we going to be given on an exam as part of our constants page? We have that naming thing. Okay. We're also going to be given this page right here, and we'll explain how to use the various parts. But importantly, as long as we can determine that we have an octahedral, we should know that our crystal field splitting diagram has 2 high energy orbitals and 3 lower energy orbitals. Okay? We'll see that that splitting is different depending on the geometry. All right? We're only covering the octahedral right now. Again, our octahedral has 2 high energy and 3 low energy orbitals. All right, so again, this is our constants page here. We just got to identify for our geometry what that splitting is going to be. All right. All right, and so titanium, how many electrons am I going to fill into this diagram here based on my electron configuration for the titanium-3? I got 1 electron. So if I'm going to fill in my diagram here, it's just got that 1 electron in that first box. Remember, we fill in from low energy to high energy. So I only have 1 electron. I'm going to draw that 1 electron in my orbital there. Okay, so one of the things we said is that our crystal field theory explains the color of these complexes. So why is that? Okay, so color. Means that photons. What do I mean by photons? Anybody know? What's made of photons? Light, right? So photons, those are what are streaming down from these light bulbs right here. They're bouncing off of me and back to your eyeball. That's how you're able to see me up here. Okay? Color means that photons are being absorbed. So this white board right here looks white to you because every single one of the photons coming down from that light bulb bounces off and into your eyeball. The blue writing appears blue because the photons bounce off, but a few of them get absorbed and only the rest of them make it back to your eyeball. Those missing photons are what we perceive as color. Evolution has kind of tuned us to have these little detectors that can tell whether we're seeing the full spectrum, which looks white, or whether there are certain photons missing, which is what color is, right? So different photons are missing if it looks blue, than if it looks red, than if it looks yellow, right? But that's just your eyes perceiving photons that are missing because they were absorbed by that material, the dyes in that blue. Okay, so color means that photons are absorbed all right. When a photon gets absorbed, when a compound, a molecule, an atom absorbs a photon, what it does is excite an electron. Okay, so absorbed photons what's called excite electrons. And what do we mean by excite? Meaning it promotes the electron from a low energy orbital to a higher energy orbital. All right, so what do I mean by that? We have our titanium ion here, right? Titanium-3, it's got this one electron sitting in this lower energy orbital here. We have a photon that comes along. We represent photons H nu. Okay, that's usually the symbol meant to indicate light. What's going to happen is that this complex is going to absorb this photon, kicking this electron from this low energy orbital up to this higher energy orbital. Okay, that would be an excitation. All right, so the electron moves from low to high. Again, that's what we call an excitation. All right, from there, these electrons quickly relax back down, and then they'll just sit there and absorb more photons, right, being kicked up. That's why this thing doesn't look blue for a second and then, fades to a different color. It's continuously blue. The electrons are just continually being excited, then relaxing that back down. Being excited, relaxing back down, continuously absorbing these photons, right? So again, this wavelength of light comes along. It kicks this electron from a lower energy orbital to an upper energy orbital, and that's the excitation of that electron that leads to that photon being absorbed. Okay? The difference in energy between these here, represent that with this uppercase delta. This is what we call the crystal field splitting energy. Crystal All right, so the delta is our crystal field splitting energy. This is the difference in energy between the low and high energy orbitals. All right. And so again, it's like, all right, what the heck? How is this explaining color? Okay. Importantly, the energy of the photon that's absorbed has to be equal to that energy that it gave the electron, right? All that energy can't be created or destroyed. It can only be transferred. So it was transferred from that photon into that electron, promoting it up to that upper orbital. So that energy of my photon is equal to that crystal field splitting energy. So that means that for these transition metal complexes, by monitoring what photons are being absorbed, we can actually measure that energy difference between those orbitals. Okay? The energy of a photon is something that was well established by Einstein and crew as being what's called Planck's constant times the speed of light divided by the wavelength. All right, H is again Planck's constant. I think it's a C, I don't know. The C is the speed of light. And this little fancy thing here called a lambda stands for the wavelength of the photon. All right. So one of these instruments you would have used in lab, I imagine, is what's called a spectrophotometer. Okay. Very kind of simple instrumentation. All right. So how these work is you have this light bulb. You take your sample. They sit in these plastic, or can be made of different materials, but these things called cuvettes. Okay, so here's our sample in here. Let's say that we have this nice, pretty colored sample. Okay, so what you do is you have this spectrophotometer. It's got this light source. It's going to shoot all these different photons in here of every different wavelength. All right, so here's the 600 nanometer, 500 nanometer, 400 nanometer. Sends all those photons in, and then it measures what comes out the other side. There's a detector on the other side. That's measuring exactly what comes out. And again, if something has a color associated with it, it's because it's absorbing certain photons. So let's say that I send in one with 600 nanometers, one with 500 nanometers, and one with 400 nanometers. And what comes out the other side is only the 6 and the 400. That means that 500 nanometer photon is absorbed. All right, and again, so why is that so cool? Because then you can say, well, if that photon got absorbed, that's equal to my crystal field splitting energy. Now I know the difference between those orbitals in my titanium, whatever, my hexa aqua titanium 3. Right, so now we're going to use this Planck's, or this equation for this photon, hc over lambda, in order to figure out our crystal field splitting energy. All right, so these are all values that are also given on your constants page. H is is super tiny number, times 10 to the negative 14 joules per second. C is 3.00 times 10 to the 8 meters per second. All right, and then since our wavelength is in nanometers, we're going to have to use the fact that 1 nanometer is 10 to the negative 9 meters. All right, so now we're just going to plug in our variables to figure out our crystal field splitting energy. Again, I do have to convert from nanometers to meters so that my units all work out nicely. What up?
Isn't Planck's constant 10 to the negative 34?
Yes, it is 34. I cannot read my own writing here. Sorry. Good call. All right, so we would get 3.9756 times 10 to the negative 19. And what are my units going to be? All right, so first of all, we're talking about an energy, so they should be units of energy. If we look at our units in our problem, nanometers cancel out, meters cancel out, seconds cancel out, so indeed I'm left with joules. And specifically, these are joules per packet of light absorbed, right? Per photon. All right, so we can also express this in joules per mole is usually a more helpful quantity. So then we would take this and multiply that by Avogadro's number, the 6.0221 times 10 to the 23. All right, or 239,000 joules per mole. All right. So the last thing that we can do from our constants page here, all right, given this color wheel, okay, where in this spectrum is the wavelength of light that got absorbed? What do we say the wavelength was? 500? So between 4 and 6, okay? So 500 nanometers would be like around right here. All right. What's really weird is what is absorbed. So we absorb this 500 nanometers. What your eyeball perceives is actually the complementary color, the thing on the opposite side of the color wheel. So if this is what's absorbed, we would actually observe our titanium solution to our hexa aqua titanium 3 to be red. Okay? So what is observed is complementary to the photon absorbed. All right, and again, by complementary, I mean the opposite side of the color wheel. Okay. So let's just say that something absorbed at 450 nanometers. What color would I observe? Absorbed at 450, so I'm going to find 450 on my spectrum here. That'd be about here. What's observed is the complementary color, so in this case, orange. All right, so we can kind of build off this a little bit more next time. For right now, let's just do another example from scratch here, sort of what you would be expected to do. Okay. Where do I want to go? right, I want you to tell me the oxidation number and finally the electron configuration of our transition metal in this complex. Okay. Everybody take a second to copy down this formula. Let's go note what the charge on my ligand is. All right, so FeCN6 minus 4. Each of those cyanide cyano groups have a charge of -1. So then what is the oxidation number on my iron? Right, remember how we figured this out? We're going to have to look at each of these ligands. We have 6 of them. Each one has a charge of -1. So that's going to sum up to -6. And what do the sum of my oxidation numbers have to equal in this compound? That net charge of -4. So then what? -6 gives you -4 plus 2. All right, so given our formula, we figured out our oxidation number. Now that we know our oxidation number, we can turn around and draw our electron configuration. All right, I should have 1, 2, 3, 4, 5, 6 3d electrons and 2 4s electrons, but then I remove those 2 4s, leaving me with just 3d6. Whoops. And then given the fact that we have 6 ligands, which crystal field splitting diagram are we going to use? The octahedral one. All right, so FeCN6 minus 4. And we're going to draw our crystal field splitting diagram. With 3 lower energy orbitals and 2 upper energy orbitals. All right. And then the last thing that we're going to learn how to do is to fill in this diagram with our electrons. How many electrons am I going to fill into this diagram? Okay. Now, before we can do that, we got to talk about the difference in the ligands here. We see that we have what's called this spectrochemical series down here. What is this thing doing for us? Okay. This ranks all of these possible ligands in terms of their splitting energy, where over here, right? This is my crystal field splitting energy. This side is the smallest delta. And then over here, these are the largest delta. And we see that there's this cutoff here. Okay? These are what we call low spin ligands. And these are what we call high spin ligands. So for our current example, which one do we have? A low spin ligand or a high spin ligand? We have this cyanide here, this cyano group. So that's going to be a low spin ligand. What does it mean to be low spin? We're going to fully fill lower energy orbitals first. So if I go to my diagram here, I'm going to start by fully filling those lower energies before moving on to the upper energy. Since I have 6 electrons, remember we're going to go through and half fill first, and then I'm going to turn around and double fill 4, 5, 6. All right, and that's because this is a low spin ligand. If we took basically the same compound here but replaced the cyanides with water, we'd have that same electron configuration. It would still be an octahedral, so we'd have that same splitting pattern. But then water is considered not a low spin ligand, but a high spin ligand, meaning we're going to half fill all orbitals first. All right, so real quick, let me make this prettier because that was really ugly. All right, so everybody just look up here real quick because I just want to illustrate the difference between low spin and high spin. Low spin, like our cyano group here, we're going to fully fill the lower energy first. So 1, 2, 3, 4, 5, 6. For high spin, you're going to half fill everything before you start doubling up. So I'm going to go 1, 2, 3, 4, 5, then start doubling up 6. That's the difference between low spin and high spin. Low spin, fully fill low first. High spin, half fill everything first. All right, cool. We'll pick back up. We'll review this next time. But yes, this is this crystal field splitting diagram.